Part D.
Part D.
Yeah.
The optional one.
And yeah, no, so on.
Yeah, I also make a special point, right? I say, just tell me the physics of the branch point contribution. Don't have to get all the amplitudes correct.
So can you please draw the path for us?
So this 226, 2.6.2, right? 2.6.2. Just for the transmitted wave, right? 2.6.2. Equation 2.6.2. And then 226 is the problem, right?
Yeah.
226 plus D, right?
Yeah.
And then you're asked to find the asymptotic extension of this thing. P1 to PE. E to the minus I, K to Z plus 2B, 1. Plus I, K1 Z, B1, right? You're asked to find the asymptotic expansion of this integral. Am I right? So the thing is that I think I asked you to make B1 equal to 0 so that the dipole is right on top of the interface. Okay, so Z is equal to minus D1 is equal to 0. Then you look at the phase function that comes from here and here. So you need to determine the phase function using this expansion I K to Z, Z plus 2D1. But actually D1 is 0, so this is equal to 0, but Z is always negative, okay, because it's dealing with lower half space. So this phase function is no different from what you have seen before, okay? So what you have studied in class is the phase function that looks like this. We have studied this in great detail, right? So by inspection, you can say that the setup point of the stationary phase point is given by K2 sine of theta. The theta will be this angle. Theta will be given by Z and rho. This will be your theta. Okay? So that is the place of the setup point. Then there are two branch points in the integrand, K1 and K2. So let's assume that K2 is larger than K1. Assume that K2 is larger than K1. Then if you draw this thing, K2 will be somewhere out here, K1 is somewhere out there. And then what happens now is that you can introduce a branch cut. The branch cuts will look something like this. For the lossless case, it will be hugging the two things very carefully, or very tightly. And then depending on your observation angle, the setup point can go all the way from here to here. Okay. So one example is to have the setup point here. Then the steepest descent path has to wrap around this K2 in this manner, just like the K1 case, just like the upper half space case. And then over here, it crosses two branch cuts. There's a two branch cut that crosses. So it must be at the bottommost Riemann shape. And then here it crosses two branch cuts again, so it emerges to the top Riemann shape, and it goes to the asymptotes. Then you are supposed to find the asymptotes are given by theta. This angle is theta. Okay, so this is one possibility of the steepest descent path that goes through the setup point. So if you want to draw it more nicely, maybe it should be something like this. Okay? So you can defer from SIP, the summerful integration path, to the steepest descent path very easily. Okay, very easily. You can see the detour and the deformation. The second case is slightly more complicated. If this is real K row, this is imaginary K row. Okay. So the second integration path is possible if this one, say if K2 is over here, K1 is over here, and the setup point is here. Setup point is given by K2 sine theta, so it can be anywhere between 0 and K2. And you can go through the steepest descent path. The steepest descent path does not depend on K1Z branch cut. So it should look something like this. Okay? But over here, there's a branch cut that goes something like that. And then there are two branch cuts that go along the shore. So if you look at this part of the steepest descent path, it only goes through one of the branch cuts here. So it goes to the bottom Riemann sheet of the K2Z branch cut. Okay? But then when it's over here, it actually encounters two branch cuts over here. So it emerges from the bottom Riemann sheet of the K2Z branch cut, but still stay at the bottom Riemann sheet of the K1Z branch cut. Okay? So here it is actually in the wrong Riemann sheet. So you cannot actually deform from SIP directly to this SDP. This is SDP, right? You cannot detour from SIP to SDP. So what must you do? You must add an additional path. Okay, you must add an additional path. The additional path is the path that goes through the K1 branch cut, or K1 branch point. You can see that SDP that goes through K1 will look something like this on the topmost Riemann sheet. And in here, I guess, am I right? I guess, no, let's start from here. It will be at the topmost Riemann sheet over here. Okay, and then here it crosses two branch cuts. Okay, so it will be at the bottommost Riemann sheet. Okay, and then here it emerges to the topmost Riemann sheet again when it goes around this thing. And it crosses this branch cut one, so it's in the bottom Riemann sheet of this K2Z branch cut. Okay. And then it goes to a Riemann sheet that is the same as this one. These two now share the same Riemann sheet, on the same Riemann sheet, so they can be connected together. Okay? And now you can detour from this path, SIP, to this path, plus this part, 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 plus this part. And then they are all connected now. So this is a contour deformation that you should do. Okay, this is a complicated one. And in this scenario, the K1 branch point will contribute. And then ask you in the optional part, just tell me the physics of this K1 branch point contribution. What happens is that the integrand will be evaluated with K rho equal K1. And it produces a special kind of wave, called the surface wave or the lateral wave. And that's the only thing I want you to say. Okay, but the contour deformation will look something like this. Okay, is this clear?
If I draw from left to right, so the integration path is the solid line from left to right, like your example in your.
This is uppermost sheet. Yeah, I actually have an example for leaky waveguide. Something that looks like this, right, in the textbook. Okay, where K1 and K2 are something like this. And then here you cross the branch cut 2 times. So at the bottommost Riemann sheet, here you cross the branch cut 2 times again. So you have the uppermost Riemann sheet. Here you cross only one of the branch cuts. So in the, not the bottommost, but one of the lower Riemann sheets. Okay, here you cross it 2 times again. It does not bring you to the top. Okay, but bring you to the sheet that is exactly this one. Because to get to this sheet, you cross a branch cut once and then you cross a branch cut 2 times. Here you cross a branch cut once, you cross it 2 times. So these two are on the same sheet. Okay? Because if you follow the tour, okay, follow the tour of this path, you're on the top Riemann sheet, cross the branch cut once, you're on some middle Riemann sheet somewhere, cross the branch cut 2 times, you're in some Riemann sheet somewhere. And in this scenario, you're doing the same thing. Cross it once, and some Riemann sheet somewhere. Cross it 2 times. So these two are the same part of the Riemann sheets. Okay, they can connect to each other. Okay, so you need to think a little bit, but after you think about it, it becomes clear. Right? What?
No.
Yes, Junu?
How does the path cross the branch cut 2 times at the K1 point?
At the where?
At K1 point.
K1 point, here, the branch cuts are like this. There's one that goes like this. That's one branch cut, right? There's another one that goes like this. So on this line over here, the 2 branch cuts. If I draw it expanded with some loss, then it will be something like this. K1, K2, K1. So over here, these 2 collapse to 1 in the lossless case. They collapse to 1. So there are 2 branch cuts here. So when you go from here, there's 2 branch cuts here. There are also 2 branch cuts to the left of K1. Right? Those are these 2 collapse to 1. Right? So you cross 2 branch cuts over here. So you emerge in the top Riemann sheet. Right? Can you see? 2 branch cut here, 2 branch cut here, 1 branch cut only here to the right of K1. Okay. And then you cross 2 branch cuts again. Okay. And then you cross 2 branch cut back and then 1 branch cut and then you back to the top. Okay. So all of them are connected. Yes?
Okay, so initially you pass you pass 1 branch cut, right?
Where?
Initially,
Here.
yeah, there.
Here there's only one branch
Right,
cut.
so-
This one.
So which means you go from the top Riemann sheet of K2 to the bottom Riemann sheet of K2.
Right.
So you move there,
Right.
and at that point you'll get the bottom Riemann sheet of K2, and you'll go to the top Riemann sheet of K1. Right?
No, you can maybe take this picture over here. You go to the bottom Riemann sheet of K2. Okay. And then here you cross it, you go back to the top Riemann sheet of K2. Here you're in a solid line again. This thing and this thing are the same sheet. Here you go to the bottom Riemann sheet of K1. Okay, bottom Riemann sheet of K1, or top Riemann sheet of K2. Okay, so some Riemann sheets in between. Okay, so you can count.
Can you please repeat how you went back to the top?
Well, here you can see I cross a branch cut once, and in the bottom Riemann sheet of K2 branch cut. I'm on the top Riemann sheet of K2 branch cut. And here I'm at the bottom Riemann sheet of K1 branch cut, but see the top sheet of K2. Okay? The same scenario goes here, except I collapse everything into 1 branch cut. That scenario there is the same as this scenario over here. Whereas here I draw the 2 branch cuts together. Okay? Yes?
So I think we only need to cross the Riemann sheet 4 times for this problem.
4 times?
Yeah.
I don't know. How many times have we called? 2 times, 1 time, 2 times, many times, right? More than 4 times.
Yeah. I think for the lossy one, we can only cross the Riemann-Schutz 4 times. And
1, 2, 3.
Yeah.
Maybe come back here.
No, come back the lower space.
I have to come back here, right? Come back like this. So I have to come back here, cross it again, cross back here. Okay, and then in the top sheet of this. And then on the top sheet of this. Okay, something like this, okay. So you can put in loss if they're the same. Okay, so they should be the same. You have to think about it. Maybe you think about it, it becomes clear. Okay? You have to, this kind of thing needs some meditation and thinking. And after you meditate and think about it, it becomes more sophisticated. Okay? So you have to think about it. Okay? If you're happy with it, I'll move ahead. I'll move ahead and teach something new today. As I say, I'll give out a take-home exam this afternoon, and then you will have 1 week to do the take-home exam. I will give you 2 days off next week. Next Tuesday and Thursday, you don't have to attend lectures. Okay, you can spend all the time on doing your take-home exam. You can hand in your take-home exam at the end of Thursday. I'll be in town next week after Wednesday. Okay. So we've been talking about FDTD and E algorithm. Today I'd like to talk about discrete electromagnetic theory. Okay, it follows from E algorithm. Okay, but written in a form that I think is very elegant. So I'd like to teach you the elegant form of EM theory. And so this is based on a paper I wrote many years ago, and I found that it's quite useful. A few of my students have used it, and they have found been able to do computation with it quite easily. So the thing about E algorithm is that, as I told you before, it actually is an algorithm that lives on 2 staggered grids. 2 staggered grids, and you can draw the staggered grid somewhat like this. And there's 1 grid for the E field. And then you can think of a staggered grid for the magnetic field. This is where the E field lives. The E field will live on this kind of grid, and so on. And then there is a grid in which the magnetic field lives, and they live on the staggered grid. They look something like this. And then we connect the magnetic field grids. Okay, they also form a rectilinear grid. So this is where the E field is. And this is where the H field is. So you can think of the staggered grid, okay? 2 of them interlaced with each other. And it turns out that you can write down a very nice electromagnetic theory on the lattice that is actually quite elegant. But before I do that, let me do some discrete calculus. Okay, let's do some discrete vector calculus. And before we do that, let's study what the difference is. And let me see. The difference, a finite difference, in terms of in a continuum world, we will have this as a partial derivative I will use this notation as many mathematicians do to stand for partial x. Okay. Then a finite difference approximation of this is that this is assumed to be valid at a half grid point, and this is approximated as 1 over delta x times f of m plus 1 minus fm. This is called a forward difference. I will denote this as a 4 partial x. Okay. This tilde here means this is a forward difference, and this is a 4 partial of x. Okay. Similarly, I can also denote the finite difference as backward. And let me write this as fm minus fm minus 1. And this is called a backward difference. I'll denote it with a notation called back partial x, which I denote with a hat. Okay, these are just shorthand notations. And then I will find that because of this notation, it's quite clear that the back partial x of fn minus 1, that is shifted 1 grid point over, okay, is equal to partial x tilde, which is this should be tilde, sorry, this should be tilde, the back difference, the 4 difference, and this is the back difference. Okay. Whereas I'm assuming that this is m plus 1, m plus 2, and so on, m minus 1, and this is f sub m. Okay, this is the approximation to the continuum law. F of x might look something like this, and this is an approximation of the discrete types. And the continuum law, this function might look something like this. Okay. And I define a shifting operator, z, okay, this is script z, such that when it's applied to f of m, it gives you f of m plus 1. Okay, this is just a shifting operator, Z transform operator. Z transform is a kind of shifting operator. And it's quite clear that if I were to shift the back difference, I get the forward difference. Okay, if you look at this equation, okay, if I were to shift the left-hand side, I should get the right-hand side, okay? And if I were to shift one of this, by m plus 1, what this equation says that if I shift it by 1, I get the above equation. Okay, I get the above equation. Not this equation. If I were to shift this equation by 1, I get the above equation. What that equation says. And it's quite clear that these two commute. This back difference and the forward difference operators commute with each other. You can show that very easily. You can actually do some algebra to show it, but it's quite clear once you do it. And then I'd like to introduce something called the discrete chain rule. In the calculus work, in the continuum calculus work, we have the chain rule. I'm also going to show that this exists in discrete calculus. That is that if I were to take the discrete partial of two products, AM, BM, this is the forward difference, and this should be given by 1 over delta x, AM plus 1, BM plus 1, minus AM Bm. Okay. And you can rewrite this difference. You can rewrite this difference as being equal to, let me write it down here, 1 over delta x Bm plus 1, sorry, not like this, Am plus 1 times Bm plus 1 minus Bm plus Bm Am plus 1 minus Am. You can always rearrange terms so that it can be written as such. Okay, you can see that some of the terms will cancel each other. Am plus 1 Bm and Am plus 1 Bm will cancel each other. So this is just another way of rewriting the above. But the bottom, as you can see, this is the forward difference of B. This is the forward difference of A. So you can see that by the chain rule, the forward difference of the product is equal to Am plus 1, the forward difference of Bm plus Bm times the forward difference of Am.
Something about the line, listen to the commutation relation. Is that ds head and tilde and
Yeah. Let me see what I have here. Head and tilde and head, sorry. Yeah, thank you for pointing that out. So these two commute, okay? They commute with each other. And a kind of a discrete chain rule also exists, which is interesting.
Really true.
Yeah.
If you plug in BMAM, then you get a different answer. So,
What is that?
so
I mean,
in that expression, if you instead did, if you exchange the AM and BM, the order of them, you will get a different answer.
what is that again?
So on there you will have AM plus 1.
Oh, okay. Okay, that's a good point. That's a good observation. That's a good observation. And I observed that if I exchange AN and BM, the expression on the right looks different. And in fact, you can show that this is also true. Okay, by some very simple algebra, you can show that this is also true. Yeah, this is also true. Otherwise, I will have a contradiction. So I can prove this by contradiction, or I can prove that by algebra. Okay, I can go to this algebra again and prove that this is true. Otherwise, this answer is contradictory. Because I change AM and BM, I get a different expression. Okay? So there are two discrete chain rules, and they're actually equivalent to each other. And you can also describe a discrete chain rule for the back derivative, okay, back differential. And it also has two forms. You can show that it has this form over here. And then another form that you can assume is this one over here. Okay, you can prove the second line by contradiction. Okay, this is true. These are called discrete chain rule. And because of this, I can do discrete vector calculus. I can do discrete vector calculus. Maybe I can start introducing a discrete gradient here. And to introduce the discrete gradient, I first introduce the four-word discrete gradient, or four gradient, okay, which is defined to be in a two-dimensional grid, M and N, okay, instead of doing this on the one-dimensional grid, I would like to do this on the two-dimensional grid, and define this to be the fourth gradient of f m of n, which I define to be equal to the x component partial x, the fourth gradient of f m n, plus y hat, the fourth gradient of f m n. Okay? When I do this, I just apply the one-dimensional rule that I have. And when I do this, I just apply the one-dimensional rule that I have. And m stands for x and n stands for y in the discrete world. Okay? And I just apply that in a straightforward fashion. And if I were to write this out explicitly, it would be something that looks like this: fm plus 1n minus fm n with the x hat over here plus y hat over delta y, fm n plus 1 minus fm n. Okay, just a very simple application of this thing. This I will call the discrete gradient. And I can define this operator. I can define this operator to be x partial x tilde plus y partial y tilde. And these are all four gradients or forward differences. Okay. And what you notice here is that partial x tilde of fmn will produce a value that is at the half grid point. Okay, this will produce a value that is at the half grid point. This actually is at the half grid point. Okay? And then this thing will produce a value also at the half grid point. Okay? So I can think of this fact. I can think of that this vector is not localized. This is a vector. Let me use a bar and a tilde to denote that this is a vector. It's not localized in the sense that if this is m, this is n, this is my x coordinate and y coordinate. If we start with the mn point, say if this is the mn point, so I actually have shifted my coordinate system a little bit. Then the x component is actually associated with a value here. Okay, the x component is actually associated with the value here. This is m plus 1n, and this point here is n plus 1. And the y component is actually associated with the value here. The value here is n plus half n, and then this is n plus half. Okay. If you associate the gradient with these values here, then this actually becomes a central difference. If you associate this with value at the half grid point, this becomes a central difference. It becomes a forward difference if you associate with the value here. It becomes a forward difference if you associate with the value there. Okay? But if you associate it with the value that's midway in between, this actually becomes a central difference approximation. So you can think of that gradient as being producing a vector at this point. And at that point, that is represented by central difference. Why central difference? Central difference is more accurate than forward difference and backward difference. Okay, I draw a picture before. I draw a picture to you before that I associate, if you take the difference between 2 points and 3 points, okay, you can do the forward difference, backward difference, and then the central difference is actually by taking the average of the two. And the central difference has this error, and this is central difference, this is forward difference, this is backward difference. This has an error with order delta. This has an error that's order delta squared. This has an error that's order delta. You can prove that very easily. It's proved in the textbook, but I'm sure that you've seen it proven elsewhere. And you can see the graphical proof by this picture also. Right? This line is almost tangential to this. The actual slope is actually this line here. Okay, so you can see that this central difference is second order accurate, forward and backward difference are first order accurate. So we like to make this kind of association and saying that the gradient actually produces the vector associated with this point. But then if this is the point, it actually produces a vector that's ahead of this point. I will call this G M N, the vector associated with this point, as a 4 vector. Okay, just my notation. I call it 4 vector. Because it's associated with points that are slightly ahead of the MN point. Okay, this is just a notation I introduced. And then I can also do the same thing and define backward differences again, and I will associate a vector with a point M given by this PR hat F M N. Okay, and then I will apply this to be x partial x of back vector plus y partial y for the back difference of F M N. I'll just apply this rule